Think about it. For a hospital, a data center, even a factory, a power outage isn't just an inconvenience. It can be an absolute catastrophe. So how do you make sure the power never goes out? Well, in this explainer, we're going to dive deep into the incredibly complex science of uninterruptible power supplies, or what most of us just call a UPS.
So yeah, what really keeps the lights on when things go south? Your first thought is probably, oh, it's just a giant battery that kicks in, right? But the reality is, it's so much more sophisticated than that. I mean, we're talking about a system that's engineered not just for total blackouts, but for a whole host of other weird electrical issues you've probably never even thought about.
Yeah, because making sure the power is on 24/7 without fail, it's not as simple as just plugging in a backup. No, it's a whole dedicated field of engineering. It's really a science of predicting failure and then stopping it in its tracks before it can even happen. So let's get into it and start with the absolute fundamentals. All right, Section 1, power when it matters. Look, before a single piece of hardware is even considered, every single project starts with the basics, the ground rules, what we're calling the absolute non-negotiables. So you've got these 4 big rules that you just can't break. First up, when the power switch is over, it has to be completely seamless. I mean, zero flicker, no interruption whatsoever. Second, it's got to play nice with everything that's already there, the whole building's existing electrical system. Third, and this one is a huge deal, the UPS can't create its own problems, It can't cause any electrical interference with other sensitive gear. And last but not least, it has to follow all the rules, all the safety and wiring regulations. There are no shortcuts here, no compromises, period. Okay, on to Section 2. Start with the blueprint. So with those core rules locked in, you don't just start buying equipment. No way. Every project kicks off with super careful, meticulous planning. This whole pre-installation phase really comes down to 3 key steps, and you have to do them in order. It's vital. You can't figure out the scope of the work until you've done a deep dive site survey, and you definitely can't finalize the design until you know exactly what that scope is. See? Each step builds on the one before it, all to make sure that final blueprint is absolutely perfect. And that site survey, honestly, it's like being a detective, but for the building's electrical DNA. The engineers are on the hunt for clues. What kind of gear is plugged in? Are there any sneaky power quality problems hiding in the system, like harmonics? Where are the new cables even going to run? Literally every single detail matters, because any one of them could point to a hidden danger that you've got to solve. Which brings us to Section 3, taming hidden dangers. Because, yeah, that survey, it often digs up some really complex challenges that the engineers have to design a solution for. Let's take a look at 2 of the biggest ones, something called protection discrimination and that pesky constant problem of harmonics. All right, so what on earth is protection discrimination? Let's make it simple. Think about the fuse box in your house. If your toaster goes haywire, you just want the breaker for the kitchen to trip, right? You don't want the power to your entire house to go out. Well, that's discrimination. Now, imagine that in a massive data center. It's infinitely more complex, but the goal is the same, making sure one little faulty server doesn't bring the whole operation to its knees. And this is where it gets really interesting, because this shows you that not all circuit breakers are created equal, even if they have the same number printed on them. I mean, look at this. Both of these are rated for 20 amps, but the one on the left, the responsive one, it'll trip at just 100 amps of overload. That's perfect for protecting delicate IT and telecom stuff. But the robust one on the right, it can handle a massive 400 amp surge. You need that for things with big motors, because they pull a huge amount of power right when they start up. You can see how picking the wrong one would be a disaster. Either it's tripping all the time for no reason, or even worse, it fails to protect your expensive equipment. Now for that second hidden danger, something that's often called the curse of harmonics. And yeah, it sounds pretty dramatic, but trust me, for electrical engineers, it really is. So what are harmonics? Well, the easiest way to think about them is as a kind of electrical pollution. See, modern electronics, they don't draw power in a nice, smooth, clean line. They kind of chop it up. And that creates these distortions in the electrical wave, kind of like ripples in a perfectly calm pool of water. The real problem is, as you add more and more devices, all those little ripples start to build on each other, creating this big, chaotic wave that can make sensitive equipment overheat, act strangely, or just fail completely. Okay, let's move on. Section 4, building for failure. So once you've figured out all those hidden dangers and have a plan for them, the actual installation can start. And the whole philosophy here is actually pretty simple. You have to assume things will go wrong, and then you build a system that's tough enough to handle it when they do. And that mindset starts with the absolute basics, like getting the cable size right.
I know, it sounds like a tiny detail. But using the wrong size wire, that is a recipe for disaster. It can overheat, and that's a huge fire risk. Getting the size right means the cable can handle the full load, all day, every day, without breaking a sweat. It even accounts for the way voltage naturally drops over long cable runs. It's not just a detail, it's a critical piece of the safety and reliability puzzle. And this right here, this is a perfect example of building for resilience. A simple UPS might just have one single power input, but look at the dual input design. This is a much better way to do it. You're feeding it with two totally separate power sources, and that is an absolute game changer. Why? Because it eliminates a massive single point of failure. If one of the power feeds into the building dies, the UPS basically just shrugs, keeps running on the second one, and no one even knows anything happened. The increase in reliability is huge. And of course, none of this fancy tech matters one bit without proper earthing. You might know it as grounding. This is the ultimate safety net, for real. It gives any dangerous fault currents a safe, easy path to go straight into the ground. It's there to protect the millions of dollars of equipment, sure, but way more importantly, it's there to protect the people who have to work around it. All right, last section. Section 5, the final connection. So the system's all designed, it's all installed, but you're not done yet, not even close. This last part is all about one thing, proving that everything works exactly the way you designed it to. You don't just, flip the big switch and hope for the best. No, every single hardwired UPS system has to go through incredibly rigorous testing and get certified by qualified engineers. They literally bring in special equipment to fake power outages, to create overloads, to simulate short circuits, and they measure every single response. It's all about getting that documented proof that this system is absolutely ready for a real crisis. And really, that brings us to the most important takeaway of all this. 24/7 power, it doesn't just happen. It is engineered from the ground up. So the next time you're in a hospital or you're using some online service and it just works flawlessly, take a second to remember the incredible amount of planning and precision that's humming away silently in the background to make that possible. And maybe it leaves you with one last question to chew on. What other invisible systems, engineered to this level of perfection, are we all relying on every single day without even giving them a second thought?